In 3.4, we're going to work through some examples, but let's quickly review the difference between permutations and combinations. Permutations and combinations. So the notation for a permutation is NPR. And the way we calculate that is n factorial over n minus r factorial. And when we're looking for permutations, we're selecting or we're counting how many combinations we have, and the order is important. We're selecting the combination and the order is important. So for example, if I had the letters A, B, C, and D, and I wanted to know how many ways are there in organizing those four letters into two slots. Two slots, these are my choices. Each number can only be used one time, and the order does matter. So if I have 4 items, there are 4 things that can go in the first slot, and 3 things left to go in the next slot. And our multiplication rule says if we multiply those together, that tells us how many ways there are of doing that. So let's see, how does that apply? How does that relate it to a permutation? So remember this exclamation mark, that means factorial. Here, we're doing a permutation. An A and a B is different from a B than an A. That's why it's a permutation, not a combination. We have 4 items to choose from, and we're choosing 2. So the way we calculated it is 4 times 3, but how does that apply to our formula? Our formula says do 4 factorial divided by n minus r factorial. So that's 4 factorial over 4 minus 2 factorial, which 4 factorial means 4 times 3 times 2 times 1. 2 factorial means 2 times 1, and notice those cancel. Gives us the same thing, because a permutation helps us have a tool to find out what we have done in the past in a more manual way. The first way we looked at the ways of doing that is we set up a sample space. We basically listed what are all the different combinations. We could have an A, a B, a C, or a D as our first choice. If I picked an A first, then with that A, I could have a B, a C, or a D. If I picked a B, then I could have an A, a C, or a D. If I started with a C, then I could have an A, a B, or a D. And if I had a D first, then I could have an A, B, or a C. So this is essentially a tree diagram that gives us our sample space. So AB, AC, AD, BA, BC, BD, CA, CB, CD, DA, DB, DC. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But if we get into larger numbers of combinations where order matters, then we don't want to have to make a diagram. Also, our rules of multiplication, those still apply, but this is just a more functional way of doing it by using this formula to determine how many ordered arrangements we have. So the order in this problem was significant. Now a combination, the order doesn't matter. So in a combination, A then B and B then A are the same pair. Think about if I have 4 items in a box. Let's say I have 4 books to choose from, A, B, C, and D, and I can only pick 2 books to read. A combination is how many groups can we make, and reading or picking these 2 books, it doesn't matter if we pick the A first and then the B, or pick B and then pick A. It's still the same group. So if the order is not significant, we call that a combination. Now, if we have 4 choices, our multiplication principle says, well, we have 4 choices for the first slot. That leaves 3 for the second slot, which makes 12. But some things are double counted because A, B, and BA are the same. In fact, everything gets double counted. So we would have to divide that by 2. So really, there are only 6 groups that we can make if the order we pick them in doesn't matter. Go back to this. And BA are the same. B and CA are the same. AB and DA are the same. BC and CB are the same. BD and DB are the same. CD and DC are the same. So 1, 2, 3, 4, 5, 6 unique pairs. So that's what we call a combination. So in this case, we have 4 to choose from, and we're filling up 2 slots. So the formula for a combination says to take n factorial over r factorial times their difference factorial. Very similar to a permutation, but we have an extra term on bottom. We have this n minus r on bottom in addition to the r, or I'm sorry, we have the r on bottom in addition to the n minus r that showed up in the permutation. So for our problem, it'll be 4 factorial over 2 factorial times their difference factorial. So 4 times 3 times 2 times 1. 2 factorial, that's 2 times 1. And this, 4 minus 2, that's 2 factorial. So those cancel, leaving us a 4 times 3 on top, which is the number of ways of picking 2 books. But since several of those got counted twice, we still have to divide by 2. So 4 times 3 over 2 times 1, which reduces to our 6. So we just have to keep up with which one of these do we need. If the order does not matter, if it doesn't matter which gets picked first, we do a combination. If the order does matter, then... So let's go and look at some of the homework problems in the book. So let's take a look at number 20, and this just wants to know, I'm sorry, let's go back to 16, we'll do 20 in a minute. 16 just wants to know, do we need a permutation or a combination? 16 says the number of ways a 4-member committee can be chosen from 10 people. So we have 10 people that we're picking from. So we have a group of 10 people to fill 4 slots. Now, at the end, unless you just go back and check the records, most people are never going to know in which order those committee members were picked. And other than possibly having a chair on the committee, one seat is just as important as the other one. So here, order doesn't matter. It doesn't matter if we have Tom, Jane, Sue, and Ellen, or Sue, Ellen, Tom, and Jane, or whoever I said. The order is not significant. So that one is going to be a combination. How many different ways are there of picking those? Number 18, the number of four-letter passwords that can be created when no letter can be repeated. But if we're making passwords, the order is important. A, B, C, D, and D, C, B, A are two different passwords. Those are significantly different. So there, since the order is important, that is a permutation. So let's look at number 20. Number 20 says 8 people compete in a downhill ski race. Assume that there are no ties, and how many different orders can the skiers finish? So we have 8 competitors, and we want to know how many different ways are there of them finishing. Well, when you're racing, the order is important. There is a difference between finishing first and second, or first and last. So this would be a permutation. Now the wording on this one may make this a little bit tricky, but if we have 8 racers, we also assume that we're going to have 8 finishers. So as a permutation, we have 8 people, and when we get to the end of the race, we're going to have 8 finishers. So out of 8 people to pick from, we want to know how many ways are there to arrange those 8 people. Now let's make a comparison. If we said we have 8 racers, and we want to know how many ways are there of filling the podium, if the podium has 3 spots, then our permutation would say out of 8 people, how many ways are there of getting a podium of 3 people? Of course, still the order matters because getting first and getting third are 2 different things. So in that case, we're only choosing 3 finishers to go on the podium out of the 8. But if we're ranking first through 8, then we, out of 8 people, we're ranking all 8 of them. So our permutation would be 8 factorial divided by their difference factorial. Remember, the generic formula is n factorial over n minus r factorial. So their n minus r is 0. Well, one thing that is kind of strange, 0 factorial by definition is 1. Seems like it would be 0, but it's actually 1. So we have 8 factorial over 1, or just 8 factorial, which means 8 times 7 times 6 times 5, all the way down to 1. Now some of us have a factorial button on our calculator, so we would just do 8, hit the factorial button, and it would multiply those together for us. So 40,320 ways of those 8 people finishing the race. 40,320 different orders that those people could finish. Now, while this was not one of the problems, let's look at the second one that I mentioned, which is how many ways are there of getting first, second, and third place out of those 8 people. So the order is important, but this time we're only looking at the top 3 spots. We don't care how the rest of the people finish. We're just concerned about who finishes first, who finishes second, and who finishes third. So this is n factorial over their difference factorial. So 8 factorial over 5 factorial. This is something we can do in our calculator. One thing you may notice, I hope if I could count, is that on all permutations, if we were to list out the things we're multiplying together, we're going to get to a point where all of these and all of these are the same. So those cancel out. Which, this just goes to our counting principle that we did sections back. If we cancel those out, notice we're left with 8 times 7 times 6. If we have 3 spots, there are 8 possible winners, which leaves only 7 choices for the second place, and 2 people have already finished, so there are only 6 people that could finish in third. So we get that same product. 8 times 7 times 6. So 336 different possible podiums if we have 8 racers. It's just the first 3 numbers from 8, counting down, multiplying them together. All right, let's look at another one. Let's look at number 24. There are 16 finalists in a singing competition. The top 5 singers receive prizes. How many ways can the singers finish first through 5th? Again, the order does matter here. So this is a permutation. So out of 16 people, we want to find out how many ways are there of not only being in the top 5, but being first, second, third, fourth, or 5th. So the order matters. So out of those 16 people, how many ways are there to arrange those in groups of 5? So 16 factorial goes on top. 16 minus 5 factorial goes on bottom. So 16 factorial over 11 factorial. This time I'm just going to do that in my calculator and do 16 factorial divided by 11 factorial. And we get 524,160. So there are a lot of different ways we could fill the top 5 if we have 16 people to choose from. Let's look at let's see. Let's look at number 28. 28 is different than the other ones we've done. You're putting 9 pieces of blue beach glass, 3 pieces of red beach glass, and 7 pieces of green beach glass on a necklace. So we have, what are our colors? We have blue glass, we have red glass, and we have green glass. So we have, I believe, 9 of these, 3 of these, and 7 of these, and we're going to put these on a necklace. So the first piece could be either blue or red or green. Then the next piece could be either blue or red or green. Then the next piece could be either blue or red or green. But notice once we've done 3 pieces, we might have used all of our red already. So then what? Well, this is a case of what is known as distinguishable permutations. Distinguishable permutations. If I do a red and then a blue and then a red and then a green, notice there are 9 different choices I could have for that one. And there's really not a difference between one of those and the other one. So in that sense, the order doesn't matter because I have 9 of those to choose from, and it doesn't matter which of those 9 pieces I pick. I have 3 different red ones I could pick from, and it doesn't matter which of those I pick first. And I have 7 different green ones that I could pick from. Doesn't matter which of those I get first. So, just for sake, I might call these blue 1, blue 2, blue 3, etc., green 1, green 2, green 3, etc. There's nothing to distinguish with whether I get blue 1 and then green 2, or whether I get blue 2 and then green 1. Those are not distinguishable. Assuming that the pieces look identical, they're just different colors. These 2 examples are not distinguishable. So how are we going to do that? If red, green, and blue are different things, but in each category they have items that order doesn't matter. So the way we're going to do that is we're going to take the total number of pieces and we're going to divide by the number in each category. We're going to do the factorial for each one of those. So in this example, we have 12, 7 more. So we have 19 total pieces. So we're going to do 19 factorial on top. So if we just did 19 times 18 times 17 all the way down to 1, that would take care of how many different ways are there of arranging these 19 pieces of glass onto a string. But since a lot of those combinations are going to look identical, because it doesn't matter which piece of blue glass we pick the first time and which piece of red glass we pick and which piece of green glass, we're going to have a lot of necklaces that look exactly the same, but we picked out in a different order. So the way we make up for that is we take, well, how many pieces of blue are there? We're going to divide out that amount factorial. How many pieces of red? We're going to divide out that many factorial. And how many green pieces? We're going to divide that out factorial. So this is still going to be a lot of combinations, but not nearly as many as it would be if we just said every one of these is different, put them in order. Well, these 3 things are different, but all of these are the same, all of these are the same, and all of these are the same. So if we do 19 factorial, we're going to divide that by the result of that thing. So I'm going to put in parentheses 9 factorial times 3 factorial times 7 factorial. So that's what we're dividing by. And when we do that, we get 11,085,360. Still a lot, but not as many as if every bead was completely different. Now let's look at number 32. Number 32 deals with selecting a jury. It says from a group of 36 people, a jury of 12 people is selected. How many different ways can a jury of 12 people be selected? Or another way of saying it is how many different juries could we pick if we have a total of 36 people and we're only keeping 12? Now, it doesn't matter the order we pick them in. This is the group, the population we're selecting from. It doesn't matter if we pick this one first or this one first or this one first, as long as we end up with certain ones in our group of 12. So we want to know how many different juries could we pick. So since order doesn't matter, this is a combination. Out of 36, we're only selecting 12. So that's n factorial over r factorial times their difference factorial. So 36 factorial over 12 factorial times 24 factorial. So we just put that in our calculator. Divide by the result of doing 12 factorial times 24 factorial. And we get 1,251,677,700. Still quite a bit of combinations. Even though the order didn't matter on who was selected first, then second, then third, it just mattered who ended up in our group. There's still a lot of different combinations. Now let's do a probability using these either permutations or combinations. Let's take a look at number 40. Number 40 says the University of California Health Service Committee has 5 members. So first of all, the committee has 5 members. 2 members are chosen to serve as the committee chair and vice chair. So we're selecting a chair and a vice chair. So we have 2 spots to fill. Each committee member is equally likely to serve in either of these positions. What is the probability of randomly selecting the chair and the vice chair? Notice order matters here. A person being chair is different from a person being vice chair. So from 5 members, we're selecting 2, and it does matter if we put Paul in this seat or if we put him in here, because that's a different job. So that's 5 factorial over 5 minus 2 factorial. So 5 factorial over 3 factorial, also known as 5 times 4, or 20. So that's how many different ways that could happen. Or we could look at that as our sample space. If we made a list of all of the ways of picking a chair and a vice chair out of 5 members, there are 20 ways to do that. If we want to know what is the probability of selecting a very specific combination of those, then out of 20, there's only one way that it's going to happen. Let's say that Jan and Edgar are the chair and the vice chair. There's only one out of the 20 possible combinations that is that particular outcome. So if we do one event out of 20 possibilities, that's a 5% chance that at random we pick the right ones. So we might look at it as there are 5 people to choose from. They're going to be chosen, but I want to see if I can guess what the committee is going to do. So I'm blindfolded or I'm in a different room, and I say, I'm going to pick, and I want to see, do I get the same results that everybody else does? Or I'm sorry, the results that actually happen inside those chambers. So I have 20 combinations to choose from. Only one of those is going to be the one that is actually used. So 1 in 20, or 5% chance of selecting the one that actually gets enforced. Let's look at number 42. I like 42. It deals with food, it deals with eating. A pizza shop offers 9 toppings. No topping is used more than once. What is the probability that the toppings on a 3-topping pizza are pepperoni, onion, and mushroom? So we have 9 toppings to choose from. We can only pick 3. And we hope that it is pepperoni, onion, and mushroom. Now notice that the order is not significant here. Now, when you put your pizza together, you might prefer it to be done a certain way, but if I'm just randomly picking my toppings, one person might start out by saying, I want pepperoni and mushroom and onions. And another person might say, I really like mushrooms, so put mushrooms on there, and I want pepperonis on there, and let's put onions on there. They're going to have the same pizza. They're the same toppings. It doesn't matter if you say which order you say them in. So we need to find out how many combinations are there of getting those 3 toppings. So 9 choose 3. So that's 9 factorial over 3 factorial times their difference, factorial. So that's 9 factorial over 3 factorial times 6 factorial. So let's just do that in our calculator real quickly. So 9 factorial times divided by 3 factorial times 6 factorial. So that's what we're dividing by. So there are 84 different combinations we could get. If I have 9 toppings to choose from and I only pick 3, 84 different combinations I could get. So I want to find out if I'm blindfolded or if I've just put the list of different toppings in a box and I'm randomly pulling out one and then another one, but it doesn't matter the order. I want to find out how likely is it that these are the ones I choose. So there are 84 different combinations that we could pick. This is the specific one we want, the one that has pepperonis, onions, and mushrooms. So 1 out of 84 chances, or 1 out of 84 possibilities is the one we want. So about 0.012. So if we consider our sample space, all of the different types of pizza we could make with 9 toppings, and we only get to pick 3, there's only one of those pizzas that has the 3 ingredients we want.